Welcome to Brain Vision.
We have these different wavelengths of X-ray spectrum emitted in tungsten. So I call them lambda 1 all the way up to lambda 3 with these associated values. The K-shell ionization energy, E sub K, is 69.5 keV. So to determine the ionization energy of the L, M, and N shells, we're going to assume that these different wavelengths are the wavelengths of light emitted during the transition from K down to L, M, or N. Okay, so let's start out with the first one. So this is part A. So assuming that energy is conserved, the energy of the M shell, the energy of the L shell, plus the energy of the light that's emitted by the L shell, which is going to be hc over the wavelength lambda. So the question is, which one should we be using? Well, the longer the wavelength, the lower the energy. L shell being the lowest energy transition, right? From K to L, those two are closer together. So this is the lowest energy transition. So we're going to have the longest wavelength. So this is going to be lambda 1. And this is going to be equal to, assuming all the energy is conserved, E sub K. So rearranging this equation, we have E sub L is equal to E sub K minus hc over lambda 1. Now for E sub K, make sure that you're using electron volts. So there are 10 to the third electron volts in every keV. So it's 69.5 times 10 to the third electron volts. And hc over lambda 1, make sure you're using units of meters for lambda 1 and not nanometers. So it's 0.0215 times 10 to the minus 9 meters. And then for Planck's constant, we want to use the electron volt seconds units on Planck's constant, not the joule seconds, because we have the energy of the K shell in electron volts. So if we're going to subtract them, we need both to be in electron volts. So that's 4.1357 times 10 to the minus 15 electron volts. You can just Google Planck's constant electron volt seconds, and it'll give you the electron volt seconds version. So using these values, and of course c being the speed of light, we get E sub L equal to 11.7 times 10 to the third 11.7 times 10 to the third electron volts, or 11.7 keV. So now we just have to do the same thing for the M and the N. So E sub M, following the same manner, is going to be equal to E sub K minus the wavelength of the energy from the light at the specific wavelength emitted from going from the K to the M shell. So this is E sub K minus hc over lambda. So K is the middle one between L and N. So this is going to be the middle wavelength, or lambda 2. So this is minus hc over lambda 2. So plugging those values in, we find E sub M is equal to 10 times 10 to the third electron volts, or 10 keV. And then for the last one, E sub N, we have E sub K minus hc over lambda 3. So lambda 3 has the shortest wavelength, and the shortest wavelength means the highest energy. And we would expect the most energetic photon to be released when going from the K all the way down to the N shell, because the N shell is farther from the K shell than the L or the M shell. So plugging this in, we find that this is equal to 2.3 keV. Oh, not EV, keV. So now we're asked to draw a diagram that represents this for part B. So the lowest shell is going to be the N shell, and it has energy E sub N, which we had written above as 2.3 keV. The next highest shell is the M shell with 10 keV, so it's a little bit farther down here. So we call this E sub M. And then if you notice, the M shell And the L shell aren't too far away, 10 keV to 11.7 keV. So this jump isn't quite as far as the N to M. So it's the L shell. And then the last one was E sub k, which we were given in the very beginning to be 69.5 keV. So it's the farthest one from all of these. So we can go down a little bit farther and draw it down here. This is the K shell. So that's what our diagram would look like.